Hi guys, so time to change pace a little bit here. We've done an awful lot of math in this course, but that's really the end of the math now. This final unit, we've got a few different items to cover, and now it's really more just about a theory course. Let's learn some theory, gain some understanding of a few different aspects of electricity, okay, moving beyond math, okay? So I've only got the 3 lessons here. If you've already gone to Blackboard and printed off the PowerPoints or taken a look at the PowerPoints, you'll see that they're kind of lengthy. Not sure how long these videos are going to get. We'll see how difficult it is for me to upload this information. But let's just move into the material and we'll see how the technology cooperates as we go along. So this lesson is about magnetism. Okay, so the first point there, the question is, why do I have to learn this? And the first point says that a good understanding of magnetism is of major importance in the study of electricity because it's almost true to say that you can't have one without the other. Now, there are some details that we're not going to deal with in basic. That'll come back in advance, and we'll get into that conversation. But essentially, anytime you have an electric current, you have magnetism, okay, and that's not essentially, that's true, okay. The other side is a little bit more difficult to say that when you have magnetism, there is electricity. There's a little bit more to the conversation, but for the time being, it's fair to say that you can't have one without the other, okay. So it's almost a byproduct, okay. So let's start with the statement that I made that is true. Every time you have current flowing through a conductor, you're going to get a magnetic field as a result of that current. Okay, it's almost a byproduct, but we've taken advantage of this byproduct and we use it over and over and over again. So the final bullet there gives you some examples of electrical devices where we use magnetism to our advantage. Okay, motors. This is what makes a motor spin. Okay, it's magnetism that spins a motor. Okay. Generators, that's how we generate electricity, is through this interaction between electricity and magnetism. Transformers, okay, they work entirely on magnetism. We will learn about transformers again in advanced electricity. There's an awful lot about transformers, okay. And then controllers, relays, and meters. So you've all got your meter, okay. It actually requires magnetism to do some of the work that it does. Controllers and relays, that's a conversation for another course, okay. But over and over and over again, there's examples of electrical devices that take advantage of the fact that electric current creates a magnetic field. Okay, so we need to spend some time learning about magnetism. First law of magnetism, this is from grade school, okay. Like poles repel each other, unlike poles attract each other, okay. Pretty straightforward. That one's easy. Okay, the second one, not so much. That's a nasty, ugly looking equation. Again, I promised you no math, so we're not even going to try and crunch the numbers on this. It's just kind of important to understand conceptually what this is talking about. Okay, so the let me get my writing tool here. So I'll circle this. So this is the Greek letter phi, which represents magnetic force. Okay. How do we calculate that? And this is the force between two objects. Okay, so Q1 times Q2 represent the magnetic forces of those two objects. Okay, divided by K times D squared. Well, K is just a constant. Okay, don't worry about that. D squared, D is distance. Okay, so here's the point. Q1, the magnetic strength of the first object, and Q2, the magnetic strength of the second object. Either of those increase, the value for phi will increase. Okay, the distance between the two objects is a huge one. The fact that it's squared. Okay, we just looked at the result of something that's squared when we talked about I squared R as power. So distance squared means that the farther apart the two objects get, okay, the greater the change. All right, and because it's in the denominator side of the equation, as D gets bigger, phi gets smaller exponentially. Okay, so as the two bodies get further apart, or more specifically closer together, okay, you get a significant change in the interaction between the two. So that's what the second law of magnetism is about. They got to be close together for this effect to be really significant. We're just going to look at the understanding. We're not going to take the conversation any further than that. As I promised, no math. Okay, so let's get into some terms. All right, we can take any material and we can plunk it into one of three categories: ferromagnetic, paramagnetic, or diamagnetic. Okay, ferromagnetic is the term that we use to talk about materials that are easily magnetized. And there's the four primary examples: iron, nickel, cobalt, and manganese. Okay, diamagnetic, the third item, these are materials, metallic or non-metallic, which cannot be magnetized. Okay, interesting that copper is on this list. Copper is our primary conductor, but it cannot be magnetized. So there is a magnetic field formed around the copper conductor when there's current flowing through it. That's a direct relationship between current and magnetism. But the copper, the material itself, does not get magnetized. Okay, which means as soon as we remove the current, we remove the magnetic field. It goes away. All right. If the conductor was something that could be magnetized, like those listed, the ferromagnetic items listed there, iron, nickel, and cobalt, what would happen is the conductor itself would become magnetized, and when we remove the current, the magnetic field would still be there because the conductor itself got magnetized. So the fact that copper is diamagnetic makes it perfect for an electromagnet. Okay, an electromagnet, and we use these all the time, and we can simply turn it on and off, right? We put current through the copper conductor, we have a magnetic field. We remove the current, magnetic field is gone. And so we have a magnet with an on-off switch, which is really pretty awesome. Okay, and then in the middle is paramagnetic, and these are all the materials that are in the middle. Okay, they can be magnetized, all right, but not nearly as easily as the ferromagnetic materials. Okay, so you've got your three possible options. So in terms of magnets, we can put labels on them. We can talk about natural magnets, and there are natural magnets. Every fridge magnet that you have at home is comprised of what's called magnetite or lodestone, and these are materials that we can mine that are magnetic. Okay, we combine them with all kinds of other materials to make them rubbery or whatever the case may be, but comprised within that fridge magnet is magnetite or lodestone. That's what makes it a magnet. Okay, and then we have artificial magnets, and the artificial magnets can be broken down into permanent or temporary, and the permanent or temporary label that we would put on an artificial magnet is a question of how long it remains magnetized. So we've got these ferromagnetic materials: nickel, cobalt, iron. There's a couple of others listed there. Notice aluminum is on that list. And once we magnetize these, they remain magnetized for extremely long periods of time. Okay, so nothing's exactly permanent, but we're talking about, potentially eons, not years and decades, but eons, potentially. Okay, on the other hand, we have temporary artificial magnets like soft iron, and they do remain magnetized for a short period of time. And now we might be talking minutes or days or weeks. Okay, so there's a fairly broad range involved here as well in terms of labeling temporary or permanent, but it's a question of, the term is retention. Okay, how long does the material retain its magnetization after it's been magnetized? Okay, and then electromagnets, and here is exactly what I was talking about, electrically induced magnetism. Okay, which means, like I said, when you put current through a conductor, you get a magnetic field. So an electromagnet is simply a conductor which we put current through, or we stop putting current through to turn the magnet on or off, and we call these electromagnets. So natural magnets, I'm going to go through this fairly quickly. I think you guys can read it more slowly if you want, but it pretty much should sum up what I just said. Natural magnets are naturally occurring. Unsure really what caused them to become magnetized in the first place. They were used originally for crude compasses. And the statement here says the most powerful natural magnet on Earth is the Earth itself. Okay, but I would argue that it's actually an electromagnet because it's the electrical currents through the Earth that create the North and South Pole. So it's an electromagnet, not a natural magnet, but there's an argument back and forth there. So it's here on the material for you to consider, and you can come up with your own conclusions. Artificial magnets, so permanent artificial magnets keep their magnetism for a very long time. Only 3 elements are actually ferromagnetic at room temperature: iron, cobalt, and nickel. So we've already seen these listed. Okay, so any permanent artificial magnet must contain some of this. The most powerful magnets are made from alloys. So that just means it's a mixture. There's some of this and some of that. Okay, this is not a course in metallurgy, so I'm just going to leave it at that. So there's a couple of examples: alnico and ceramics. And again, these are alloys made up of mixtures of different materials, including something that's ferromagnetic. Temporary, so they lose the magnetism almost as soon as they're removed from the magnetizing influence. Okay, so something like a screwdriver, you can magnetize the end of your screwdriver temporarily. Okay, electromagnets are a form of a temporary artificial magnet. And this will be discussed later in greater detail. There's an awful lot of time spent talking about electromagnets. Again, next term in the advanced electricity. Okay, so in order to talk about magnets, what we typically do is we look at these things called lines of force. Okay, they're invisible lines of force around a magnet. We call them lines of flux. Okay, my pictures are all 2-dimensional, but remember that this is 3-dimensional all the way around the magnet. So we talk about the lines of flux so that we can understand why magnets behave the way they do. Okay. So here we see a couple of bar magnets, and we've placed the 2 north poles together. Okay, remember that like poles repel, unlike poles attract. So we see the lines of flux around our bar magnets, and it's the behavior of the lines of flux that define the behavior of the magnets. Okay, so we can see here that the lines of flux are what's pushing against each other, which is causing the north poles to repel. So there's some arrows here. I've got more details. Let's just move on. We'll talk about like poles repel. Yes. Magnetic lines of flux, lines of force or lines of flux, they all behave consistently. So we have 8 characteristics of the lines of flux. So the first one is that they always form closed loops. I'm hoping this works when I do this video. Hang on, let's see what happens when I click this. Absolutely nothing. All right, that's what I was afraid of. So let's go through the list and then we'll talk about each of them. This is supposed to create a link to that slide, but that's not going to work. Let's carry on. Always form closed loops. They never intersect. They travel north to south external to the magnet. Remember in the previous slide, there were arrows on the lines of flux. This is how we define or decide which direction those arrows go. They have tension and length. This is kind of like an elastic, although honestly the exact opposite. We'll get to that in a second. They take the path of least reluctance. So just like current takes the path of least resistance, magnetic lines of flux take the path of least reluctance. They go through all things, so there are no insulators for magnetism. Parallel lines in the same direction repel each other, and parallel lines in the opposite direction tend to unite. That's the word that's cut off by this little picture of me in the corner. Okay, so that's just the list. No explanation whatsoever. So let's go through the next 8 slides and find out what these things mean. Magnetic lines of flux always form closed loops. So in the first picture I showed you, we didn't even look at the lines through the bar magnet itself, but it's important to understand that they are there. Okay, so the lines of flux form a complete loop, every single one of these. One other thing I should mention, this is now a good time, in terms of perspective. What I've drawn there are 4 lines of flux. Okay, 2 straight up and 2 straight down. Remember that this is a 3-dimensional image, so there are those lines all the way around. But in terms of magnitude, okay, this almost gives you the impression that maybe we're talking about a couple dozen lines of flux. Okay, in fact, Okay, when we go to quantify magnetism, we talk in terms of millions, tens of millions, even hundreds of millions of lines of flux. Okay, just to get you some concept of the scale. Clearly, we're not going to draw all of those. First of all, we couldn't take the time, we couldn't make them fit, and it would be far too clumsy. So this drawing here with 4 lines of flux makes it much easier for us to visualize what's happening and talk about what's happening. But just so you have a little bit of understanding, we're talking about millions and tens of millions of lines of flux, okay, hundreds of millions. Okay, so there's a lot of them, but we're going to look at typically about 4. These lines of flux never intersect. So here's the best image I have that's 3-dimensional, and we can see our lines of flux all the way around our bar magnet, and none of these ever cross. And when we get through a couple more slides, we'll understand why that is. So they travel north to south externally. So now let's put some arrows on these lines of flux. Okay, so if we were to finish drawing the closed loop, you can see that we've already decided not to bother. But if I close this loop right here, this first one, so if the lines of flux have arrows that go north to south external to the bar magnet, then there's also an arrow here going from south to north internal to the bar magnet. Okay, so the way we make the statement is north to south externally. Okay, but understand what that means when we close the loop. Okay. Next slide. Magnetic lines of flux have tension in length. So when 2 magnets are separated, they will snap back together as though they were attached with an elastic band. Okay, so it's very much tension and length is like an elastic. You stretch it, it snaps back. Okay. However, the magnetic lines of flux behave in the exact opposite fashion, because that elastic gets stronger and stronger and stronger as you stretch it, okay, until finally you reach its breaking point and it dramatically snaps. Okay, magnetic lines of flux behave in exactly the opposite fashion. So we go back to that second law, which said that as we pull the 2 magnets further apart, the force of attraction will get less. Okay, so the greatest force of attraction, the greatest tension and length happens when those 2 magnets are very, very close together. And the more we get them separated, the less tension and length we have. There is still tension and length, but the force gets much, much less. So there's not a point where it dramatically snaps. There's just a point where suddenly the force of attraction is so small that it becomes negligible and it just doesn't exist anymore. Okay, so tension and length is like an elastic, but the behavior is the exact opposite. Instead of being the strongest just at the moment before it snaps, which would be the case for an elastic band, okay, it's strongest when the magnets are closest together. Okay, and that information comes from that equation that we looked at, the second law of magnetism. Magnetic lines of flux take the path of least reluctance. Okay, just like electrical current follows the path of least resistance. So these lines of flux, so far we've looked at them and they're nice and symmetrical. Okay, but that's certainly not necessarily the case. There could be all kinds of interferences, all kinds of reasons why those lines might not be symmetrical. Okay, and we will look at a couple of examples of that. But what I've shown here is this circle is some type of ferromagnetic material, and the lines of flux are going to choose to follow that path. So where these lines of flux in air without any interference would be nice straight lines, just part of the symmetrical loop, okay, we can see that these lines get distorted and warped and follow this path of least reluctance through whatever this ferromagnetic material might happen to be. Okay, that ties in nicely to the next characteristic. Oh, hang on, sorry, I missed that. Unfortunately, sorry, what that meant, the conversation I wanted to go there, was that we can't shield ourselves from a magnet. Okay, what we can do is we can encourage the lines of flux to go somewhere else. All right, so in that previous image, if we had been standing inside that circle, there would be no lines of flux passing through our body because they would choose to detour around through the ferromagnetic material. Okay, so we cannot shield ourselves from lines of flux. Okay, but we can encourage those lines of flux to go somewhere else. Okay, sorry about that. I needed to include that conversation in the previous slide. Now we're down to parallel lines in the same direction repel. So here we are. We've got lines of flux exiting the north pole of each of our two bar magnets. And so we've got two bar magnets that are the north poles facing each other. So we know where they're going to repel. And why is that? Well, we can see where we've drawn the arrows on these lines of flux. So these are coming down and these are coming down. And so these two lines of flux right here are parallel in the same direction. Okay, same thing up here. These lines of flux are parallel in the same direction, and so they are all going to repel. And this is why like poles repel. Okay, the same would be true if we flip both magnets around and there was a south poles facing them. Okay, the lines of flux would be entering the south poles, but we would still have parallel lines in the same direction. Now, this is also the reason why lines of flux never intersect. Because if we look at the lines of flux coming from this magnet by itself, all of these lines of flux, and remember we're talking about millions and tens of millions of lines of flux, and they're all parallel in the same direction, which means they are all repelling. So that's why our cloud, if you will, of lines of flux spreads out evenly, okay, and is nice and symmetrical, because each and every one of them is pushing against all of the others. Okay, and that's why they spread out evenly, and that's why they never intersect. Okay, so that's parallel lines in the same direction. They are repelling, okay, causing like poles to repel. Parallel lines in the opposite direction, we say that they tend to unite. Okay, they'll actually pull together. So what we have here, so right here we have a line of flux, okay, which is entering that south pole. Okay, that arrow is going to be down. And over here we have a line of flux that's exiting that north pole, and it's going to be going up. So right there we have two parallel lines of flux in opposite directions. And so what they will do is they will unite. Okay, they come together, and so in the bottom image we see, and this is not the whole picture, right? Understand that we have a line of flux here. Comes all the way around there, through there, and attaches right there. And I should have started here. There we go. So north to south externally means I can put an arrow on it right there. There is one line of flux in its complete path through both magnets. Okay, and so now this is why north and south poles, this is why opposites attract, because two things happen. First of all, the parallel lines traveling in opposite directions united and turned the two separate lines of flux into a single line of flux. And now we refer back to the rule that says lines of flux have tension and length. So instead of two lines of flux, one on each bar magnet, we have a single line of flux through both magnets, and now it's that tension and length that is going to cause those two magnets to pull together. Okay, so step one is unite, step two, tension and length, and that's why opposites attract. Okay, so when we talk about magnets and when we talk about how magnets behave, okay, we can accomplish it and we can understand it by talking about these 8 characteristics of lines of flux. Okay, never mind how the magnet behaves, let's talk about the lines of flux and how they behave, and it explains the behavior of the magnets. Okay, so I think that's the end of my lesson on magnetism. All right, there's going to be lots more to come on this. In fact, even in the next lesson, which is a completely different conversation, we're going to come back and talk about magnetism a little more, because that's going to be a recurring theme from now on. When we talk about electricity in any fashion, magnetism is going to come into the conversation somewhere. Okay, so that'll do for this lesson. I'll be back with the next one.